me first keep the title to see what I'm actually going to talk about. Actually, I was quite ambitious when I prepared the slides, so some of the topics here will be moved to the AC Splinter meeting this afternoon. So this morning I will only start with a short reminder about the recent transition to the IGS-14 NTEX framework. And then I'll go directly to the third part, impact of the switch to the IGS-14 framework on several aspects of the IGS terrestrial frame solutions. First, their alignment to the ITRF, then their scale, and finally on the accuracy of the IGS station positions. The fourth part will be moved to this afternoon as well. Okay, let's go. So the transition to the IGS-14 framework comprises three different parts. The first one is the reference frame switch from IGB08 to IGS-14. IGS-14 is basically an extract of 252 stations from ITRF 2014 with a long and well-behaved time series. And you can see the map on the bottom left here, where we're glad to see these green dots, which are new reference frame stations in previously sparse areas like South America or South Pacific. We also designed a core network of 51 homogeneously distributed clusters of stations designed for the alignment of global GNSS solutions. And like ITRF 2014, IGS-14 comes with an innovation in the representation of the reference coordinates, which is a representation of post-seismic deformations with logarithmic and exponential functions. The second part of the switch was the update of the calibrations of different ground antenna types in the NTEX file. I won't go into the details here, but just mention that after the switch, absolute calibrations are now available for more than 90% of the IGS stations. And the last part of the switch was the update of this GPS and GLONASS satellite antenna calibrations. Regarding the radial phase center offsets, the ZPCOs, what we did is that we derived the daily estimates from the repro2 contributions of 7 analysis centers by constraining the scale to that of ITRF 2014. The ZPCO time series we got were showing clear trends, so that we decided to remove a mean trend per AC so as to bring the estimates to epoch 2010, and then we computed weighted average of the time series over all ACs. And in the end, the mean ZPCO change from IGS-08 to IGS-14 is about -6 centimeters, which induces a net scale change of the IGS terrestrial frame solutions of about +3 millimeters. Regarding the X and Y PCOs, we also derived time series of daily estimates, but their stability and the inter-AC agreement were too poor to derive reliable values, so that in the end only the X and Y PCOs of the GPS Block 2R satellites were updated thanks to the availability of pre-flight calibrations from the manufacturer. And as you well know, the new IGS-14 framework was officially adopted in January this year. So this is for this afternoon. And let's come to the impact of the switch to IGS-14 on the daily IGS terrestrial frame solutions. So this plot here shows the residuals of 6-parameter transformations between the daily IGS solutions, first repro2, then operational, and on one hand in blue IGB08, the IGB08 core network actually, and on the other hand in green the IGS-14 core network. So this is a measure of of the precision with which each of the daily solution can be aligned to each of the reference frames. And in the bottom right plot you can see the number of reference frame and core stations usable in each of the daily solutions. So what can we see here? Well, of course, the alignment residuals are notably improved. Let's say after 2010, that is when the IGB08 coordinates, reference coordinates, get more and more extrapolated. But we can also see that the alignment residuals to IGS-14 are also starting to increase, since the IGS-14 reference coordinates are already extrapolated by 2.5 years now. We can see here that the number of usable IGS-14 stations is already declining because of recent discontinuities affecting reference frame stations, earthquakes and equipment changes mainly. While the IGS-14 core network has remained fairly stable for now, and let's hope it will last a few more time. Okay, so this improved alignment to the reference frame is quite an obvious improvement due to the reference frame switch. But let's come to something more subtle now, which is the scale of the daily IGS terrestrial frame solutions. So to start, I'd like to recall how to interpret scale factors that are estimated between a set of daily IGS solutions and a linear reference frame, either IGS-08 or IGS-14. First, a mean scale offset can be expected because the scale of the daily frames depends on the mean values of the ZPCOs in the antex file, because of this correlation between the satellite phase center offsets and terrestrial scale. So as we are using conventional satellite PCOs for now in the antex file, the mean scale of the terrestrial frame solution is itself conventional and can be offset from the ITRF scale. Then a difference in rate can be expected as well, because the scale rate of the daily solutions is determined by the fact that we use constant satellite ZPCOs in the antex file. So this assumption of constant ZPCOs determines what can be called the intrinsic GNSS scale rate, and which can be compared to the ITRF scale rate. Then we also expect seasonal variations due to the aliasing of nonlinear or seasonal deformations of the station network into the daily scale factor estimates, which is sometimes called the network effect. And finally, we also expect systematic errors due to imperfections in the antex ZPCO values combined with changes in the satellite constellation. Okay, so now how does it look with real data? So in the top plot here, the cyan dots show scale factors estimated between the daily IGS solutions, again repro2 and then operational, and IGB08. The blue curve is a linear plus annual plus semi-annual fit, and the red dots below show the residuals of the fit. For the bottom plot, what I did is that I recombined the daily AC repro2 solutions after having fixed the satellite ZPCO values to their IGS-14 values in the AC solutions. So these special combined solutions have their scale determined by the IGS-14 antex, and I compare them to the IGS-14 reference frame. So what can we see here? Regarding the mean scale, there's a minus 0.3 ppb bias in the top plot between repro2 and the ITRF 2008 scale, which can be well explained by recently introduced orbit modeling changes in the IGS. While on the bottom plot, the mean scale offset is 0 at epoch 2010, which is due to the way we define the satellite ZPCO values. Remember a few slides ago when we had to correct the trends and we bring the mean estimates to epoch 2010. Regarding the scale rate, which is in both cases determined by the same assumption of constant ZPCO values, well, we can clearly see that this intrinsic GNSS scale rate is closer to the ITRF 2008 scale rate than to the ITRF 2014 scale rate, which is annoying, but, well, that's how it is. The seasonal variations are pretty much the same in both cases. And finally, what's interesting to see here is that the nonlinear non-seasonal variations which are shown by the red dots, are clearly less scattered when using the IGS-14 antex ZPCO values, especially in recent years, and that is due to improved ZPCO values, especially for recently launched satellites. Okay. Oh, and this is the last slide showing just conclusions or a summary of the scale part, so I'll let you study it at home and move to the next part, which is accuracy of IGS station positions. So we know that our station positions are biased, and this is evident because of the existence of equipment-related discontinuities. If you change an antenna or a receiver and observe a discontinuity in the time series, it's either because the position before or the position after, or both, are biased. So the questions I wanted to address here are the following. What's the magnitude of equipment-related discontinuities in the IGS Repro 2 station position time series? What does it tell us about the accuracy of the IGS station positions? And do antenna change discontinuities get smaller with the new antex file? So the answer to the first question is in these histograms, which show the sizes of a set of equipment-related discontinuities estimated during the long-term stacking of the daily Repro 2 solutions. So you could try to fit a normal distribution to this histogram, but it turns out that it doesn't work. But you get a very nice fit using student's t-distribution, which is a sort of heavy tail distribution used sometimes to model processes where values far from the mean occur more often than in the normal case. And I tried to identify different subcategories of equipment changes and see if they have significantly different sub-distributions, like antenna changes versus receiver changes or uncalibrated radomes, but I didn't find anything clearly visible, so I'll stick to overall distributions hereafter. Now, what does it tell us about the accuracy of IGS station positions? Well, the size of a discontinuity is basically the difference between the bias after and the bias before. In terms of probability distributions, it means that the distributions of the discontinuity sizes is the convolution of the bias distribution with itself. So what distribution convolved with itself gives a student t distribution? Anyone knows the answer? I don't have a theoretical answer to that, but I pay a few beers to anyone who knows. But numerically, it turns out that another student t distribution works not perfectly, but very, very well. So from which we can conclude that the equipment-related biases in our station positions follow heavy tail distributions themselves. You can see the the parameters of the distributions are estimated in this table. The degree of freedom nu is above 1 but below 2, which means that the mean is well defined, and I actually assume it was 0. However, the variance is undefined because we have many values outside far from the mean. And in terms of confidence intervals, it means that you need huge intervals to cover most of the biases. For instance, if you want to include the 99% of the position biases, you would need, according to these results, intervals as large as plus minus 2 centimeters in horizontal and plus minus 6 centimeters in vertical. And the third question was, do antenna change discontinuities get smaller with the new ground antenna calibrations in IGS 14.80x? So to answer this question, I selected a subset of 346 antenna change discontinuities involving at least one antenna whose calibration was updated from IGS 08 to IGS 14. And this gives the histograms to the left, which are consistent with the IGS 08 antex. And then I applied PPP-derived position corrections to compute what would have been the expected discontinuity sizes using IGS 14.80x, and this gives the histograms on the right. And well, we can't really see any change in the distributions from left to right, which means that the ground antenna calibration updates from IGS 08 to IGS 14 have a marginal impact on the discontinuity sizes, hence on the position biases. And therefore, the errors within the type mean calibrations that we are using do not seem to be a major contributor to current IGS station position biases. And I mean errors within the type mean calibrations and not errors due to using type mean calibrations.